So now I want to briefly tell you a bit more about the zoo of modes that one can see, and the zoo of modes and those modes that can then couple complying with phase matching. And phase matching is, first of all, energy conservation, and then momentum conservation. And this momentum conservation, now watch this here, it's changing now, changes into conservation of this m quantum number, which is the m quantum number tells you how many zeros are there around the rim for the signal, for the idler, and for the pump. And phase matching means that this has to add to 0. And these are boundary conditions for the L. Now what you can, so this is the same formula. And now if you realize that the m value, the number of modes in the azimuthal direction, is the L quantum number minus the number of modes in the what is it? The polar direction. Maybe that's why it's called P. Remember we talked about this before. Or you could say L is the total number of nodes or nodal lines, and this is M plus P nodal lines in the azimuthal and in the polar direction. So the overall kind of number is given by the L equal to M plus P. But now we can replace the M by L minus P. So this would be LS minus PS, MI minus PS, minus LP plus PP. And then you can sort this differently. And you have this, you group the L numbers together. And then this, the P's, PS plus PI minus PP, this we now call, we use this new number A. And so we now group the modes according to this. So A is called the cluster number. So the blue ones there, the A value is 0. And in order for the A to be 0, if suppose the PP is 0, then the A can only be 0 if both PS and PI are 0. So this is only this 0-0 combination. This is PS, PI, 0, 0. PS equal to 0, PI equal to 0. And here PS is 2, PI is 0, and so this is 2. So for PP 0, so 2 plus 0, 1 plus 1, this is 2. And so you can have these different slots. And remember, only for A equals 0, the cluster consists of only one on one number. And so then you have also those for which the PP is equal to 1, the PP is equal to 2, and you can you get so here if P is 1, now you have 1 plus 0 minus 1. So this is also an A equals 0 here. Okay. So now energy conservation, when you plug this in, I don't show you all the details, but this is just a formula. You can also look it up in Gorodetsky's paper. Oh, this is selected topics in quantum electronics, 2006. So when you plot the wavelengths versus temperature, this is this temperature tuning that I was telling you about, then the different clusters correspond to different curves. So if you change from A equal to 0, 2, 4, 6, these are largely different here. And within each cluster, there's a fine structure. So there are enough modes so that you can have this phase matching, but they're separate enough. So, oops, Oh, this is coming on the next slide, yeah. Okay. So first of all, once you reach phase matching as described, then you can do this experiment. Pump, take the generated light out. Maybe some of the pump is still coming out. You separate it maybe with a prism or grating, and these are largely different frequencies. This is largely non-degenerate in our case here. And then signal and idler goes in different directions. And then we can have single photon detectors, so these are avalanche diodes, and look for the correlation between signal and idler. So this is the correlation function correlating signal photons and idler photons. And this, for equal time, is very high because they are produced jointly. And the width here tells you something about the coherence time or correlation time. And I told you that because of the narrowness of the modes, the width is in the megahertz regime, which is typically also the same spectral bandwidths associated with atomic transitions. So you see that this is well matched. What you can also do, if you have a pair, we briefly discussed this before, you can herald on one of the photons in one pair and then prepare the other. And so you post-select in the other beam. Whenever you have a trigger signal in this one beam, then you do a Hanbury-bound Swiss experiment on the other beam, post-selected. And so that means you have, in correlation with the click detection on the idler mode, in the signal, you know you have a single photon. You put it on a beam splitter and with two detectors on the two outputs. And then you could look for this correlation. And of course, this single photon can only trigger one or the other click detector. And you will see this minimum, which is called anti-bunching. I actually thought it was really interesting when in 2004, I think it was, the collaboration between Madrid and Stockholm, this group showed that when you don't have click detectors, you have a single photon coming in. If you don't have click detectors, if you have homodyne detectors with local oscillators, you can actually create correlation. The single photon can create correlation between these two detectors, which is really nice and makes you think about what a single photon is. Okay, but I'm digressing. So for applications, it's also important that the single photon is really in a single mode. And if you have two correlated beams, like out of this Chi2 process, then if you look at only one of them without post-selection, without triggering, just ignoring, not looking at one beam, just looking at the other beam, and looking at the intensity correlation of this beam, you will find that this is a thermal beam. So for a thermal beam, you know that the intensity correlation should be 2, the normalized correlation function for equal time. So G2 of 0 should be 2, whereas G2 of tau going to infinity will asymptotically go to 1. So there's 2 to 1, this enhancement at t equals 0. However, if you couple to more modes, Maria Chechova was complaining I tell so many things that maybe I should not tell this now. But this is, physics is about redundance. So if we kind of occasionally say some things which sound a bit similar, it's probably not so bad. So if you have more than one mode, it will not be 2, but it will be 1. Actually, if you want to calibrate the shot noise of a detector, you could even illuminate it with white light, which is thermal, without selecting spatial modes. And then, if you don't go into saturation in your detector, you will also see thermal statistics. You will see G2 of 0 equal to 1. only when you select a single spatial temporal mode, you go to 2. And so when you do this, so we can, first of all, go pick a particular temperature, and then you have signal and idler, and let's concentrate on one side. For a particular temperature, you will still get emission into a few modes. And as a result, the G2, with several of these clusters, so several of these modes contributing, is only 1.5 in this case. This is clearly telling you the fact that it is different from 2 is clearly telling you there are more than one modes. So if the number of modes is k, it's 1 plus 1 over the number of modes is the effective number of modes is the G2 value that you expect in Hanbury, Brown, and Swiss experiment. But here, if you now select the A equals 0 cluster, then this is only this single state. So you can do this by spectrally, this is wavelengths here. You can do this by spectrally filtering. And then you see this really goes all the way up. So you see if you pick the right mode, you really have a single photon in a real nice single mode. Okay, and then these are tuning curves in relation to different frequency bands, which are important either in communication or if you want to realize atomic memory with atoms. Then in the near infrared, there is cesium and rubidium. And you see that with our with this Western gallium mode resonator, you can couple the C band here and rubidium, for example. This is one of these curves connecting the two, or the O band and cesium. Okay. So now we have done some experiment showing that single mode, single photons can actually be used to excite cesium. This was a reference scan with some saturation peak done with a laser with a coherent light scans through. So we know the resonance that we're looking as here. And then we tune this single photon source just to this frequency. And so we can first tune the PDC by changing the pump laser frequency. And then the fine tuning can be done with the voltage. Okay, and then what you see is that this is the correlation between signal and idler. So there is the idler triggers the signal in this detector. And so this setup here, basically all the light from the signal goes to this avalanche photodiode APD. So so part of the light goes via this mirror, but it's as if all the light would be dumped here. So by correlating these two, it's just this correlation function that we had seen before with this larger peak and seeing the correlation widths. But now if instead of having a mirror here, we have a cesium cell, then you excite the cesium with a single photon pulse, and you look for the fluorescence. The fluorescence will come back, and now the fluorescence will excite the APD. And then you see the lifetime of the cesium. So this is a first experiment that shows that with this particular single photon light source, it's kind of, this is a good light source if you want to selectively couple to a particular transition, like in this case in cesium. This actually is the cesium cell with the fluorescence out of the cell. Okay, so a lifetime measurement with single photon excitation, with real single photon excitation. Okay, So now I come to the second part. Remember, I told you I wanted to talk about 3 different topics, also on the experimental side. So the one we finished now, whisper and gallery mode resonators. And the next one will be soliton pulses in standard optical fibers. And the third one will be self-induced transparency. This will be the shorter one. So solitons appear in many areas of physics. I mean, you just need the appropriate nonlinear differential equation. And so examples are in hydrodynamics, water waves, in optics, in Bose-Einstein condensates. So this is what's written here. Probably you cannot see from the back. Oh, wrong knob. Okay, so this is some waves in shallow water, and sometimes, so if the conditions are right, you can see these so-called solitary waves. So soliton comes from the word solitary, I think, so isolated waves. So in the case of water, it's a single bump. In optics, typically it will not be a single bump, but it will be an envelope, which is kind of with many optical oscillations underneath. But here in the water case, it's just a single, like half a wave. So these are, if you look at the theoretical equation, they look a little bit like quasi-particles, so they're kind of they have some intrinsic stability, and even if they kind of collide, if they run through each other, they emerge almost unchanged. So this is what you see here. There's one propagating so this is the wavefront propagating in this direction, and the other one is propagating in this direction. So there are a few beaches, not so many, where occasionally you can see this. So some people with their camera, they then go and wait for a long time until they can see a nice picture like this. So in optics, what you do is typically, to see this effect, you launch a pulse into a fiber. And the normal thing is that because of dispersion, the pulse will broaden, and if it comes out the fiber, the pulse length will have enlarged. So this is certainly true if the intensity is low enough. If the intensity gets higher, we have this nonlinear effect that we already discussed. This intensity-dependent refractive index, which leads to an intensity-dependent phase shift. So this can counterbalance the dispersion so that what comes out is an unchanged pulse, although there's dispersion in between. But the dispersion is counteracted by this nonlinearity. And for this, the conditions have to be right. There is a nice picture that goes back to Lynn Mollenauer. The first one to predict solitons in optics was Hasegawa from Japan, and Lynn Mollenauer from Utah, I think, yeah. So he was the first one to observe them experimentally many years ago, and he came up with this picture describing the effect. And so this is a mattress. No, this is a solid run path. So if you have a group of joggers and they have different abilities, and one is faster than the other, so quickly the group will disperse, and the envelope will widen and widen. So this in optics is what normally happens when you have dispersion. However, if they run on a soft mattress, so that under the weight of the joggers they will dent in deep enough, then you could say the fast ones are punished. They run uphill all the time. And if you tried running uphill here, you know how difficult it is. Anyone tried? And the slower ones, they have the benefit of being able to run downhill all the time. But the conditions have to be right, and the spread of the speeds should not be too much. It should be kind of well adjusted to the dent. Then this can happen that way. So you could say that they suffer because they always have to run uphill, but these are the people whose performance is better. You could also say they help the others so that everybody stays together. So this, I think, could be a model for a well-functioning society. And then things stay together and things stay coherent and everything is fine. Blackboard. I'm supposed to go to the blackboard. Benoit, did you put that slide in to chase me to the blackboard again? No, this was a joke. No. I know, I did. Okay. So I thought I'll use the blackboard to explain this this soliton effect. So this is a classical soliton. So if you have n equal to n0 plus n2 times the intensity, and if the intensity is changing as a function of time, then the refractive index will also change as a function of time. And why is it changing as a function of time? Because you have a pulse which is is rising and lowering. Maybe I shouldn't put time here. Let's put here x. So this is a pulse going in this direction. So this is the leading edge. And the intensity is going up. The intensity is going up, so d I dt is positive. So in the leading edge, also the dn dt will be positive, and likewise on the other side it will be negative. Now I already said when you have a propagating wave and you change. So if you introduce a stationary slab of some nonlinear, of a stationary slab of some with some refractive index, which is higher than the than air, then you will change the phase. But if you kind of change this refractive index as a function of time, for example, if you would move a wedge of glass into the beam, you have a phase which is changing with time, so you change the frequency of the beam. But you could also do this with an electro-optic modulator, of course. So then the dn dt is related to the phase change by minus lambda divided by the length over which the refractive index changes. So you would have this wave, and then you have this refractive index change. And this is propagating this direction, and this effectively, putting this in changes the phase here. And if this is a wedge, then and you move this wedge, then you have this frequency which is a changing phase, changing with time. So then this is minus lambda over L d of this phase shift dt, which is a frequency. So that means in the leading edge here, you produce in the leading edge, you produce the NDT larger than 0. You produce negative frequencies, or the frequency, you subtract some delta nu of the frequency at the leading edge. And on the trailing edge, you add, just reverse. trailing edge, the NDT is smaller than 0, so you add. So now, what happens in dispersion? Normally, in the visible, with all the absorptions in the blue and in the UV, the speed of light at the larger frequencies is smaller than at the smaller frequencies. So blue travels less fast than red. That means the slower frequency travel faster. So in this dispersion, when this pulse disperses, it's the lower frequency that appear at the leading edge. In addition, you lower the frequency even further, so both effects add up. But if you go into the anomalous regime, anomalous dispersion regime, that means, let's just say C blue larger than C red, which is not what happens in normal glass in the visible here. Then it's just reverse. Then the higher frequency appear at the leading edge. This kind of electro-optic modulation effect, this self-phase modulation of the pulse reduces the frequency at the leading edge. So the higher frequency components appear, the frequencies are reduced, so this kind of stabilizes this, and so dispersion plus self-phase modulation gives stable pulses. But these are stable in a classical world, because for these two to compensate, you need one particular amplitude. But we already saw in the first lecture that if you have a coherent light beam, the amplitudes are not, the amplitude is not fixed. You have this uncertainty, this uncertain region. So what you can do with these solitons, you can go into the soliton regime. This means that despite of the fact that they propagate like a few meters, for example, through the fiber, they don't disperse. Without this, if you are in the normal dispersion regime, then these pulses broaden within a very few millimeters. If they are on the level, the pulse width is on the level of 100 femtosecond, 200 femtoseconds, which is true in the experiments that I'm going to show you. But if you go in the soliton regime, the pulses stay together, and the nonlinearity that they experience in the first 1 or 2 millimeters, they experience throughout the whole fiber. So we make sure that this nonlinearity in glass is effectively enhanced by confinement in the transverse direction, but also in the longitudinal direction through this soliton effect. Okay, then, so this was one thing. Now, when you look at the spectrum of these solitons, so these pulses, they have a certain width, and the Hamiltonian, which is h bar gamma 3 a dagger AA, the self-phase modulation. This is this degenerate case. But I told you, especially if these pulses are very short, they have a certain spectral width, you can also allow these to be slightly different. So you can have, you annihilate two photons at frequency omega, A omega, and then you create photons, and in order to conserve energy, you have to create them at omega plus delta and at omega minus delta. So when you do this, and now you go into the spectrum of the pulse, you look at the spectrum. So let's say the pulse looks like this. So here in the center is the highest intensity, so the largest nonlinearity. So it would typically then take 2 photons. So one of the processes here is that 2 photons are taken away from the center frequency. Maybe I call it omega 0, because this is omega, so this is omega 0. And so it will be dumped into the wings, omega 0 plus delta and omega 0 minus delta. So now you can, in the experiment, when you want to understand, I mean, how much of this happens, I mean, which is this process so if this process is important, something like this should happen. So what one can do is you can plot, you can look for correlations between different frequency components. Between spectral components. I just call it spectral correlation. And so here you have omega, and here you have omega. And here you have omega naught, and here you have omega naught. And now if I can write a plus and a minus, if we think that there are the amplitudes in these particular frequency bins are anticorrelated or correlated. So a plus for correlation and a minus for anticorrelation. So this picture would say that these 2 photons at frequency omega 0 minus delta and omega 0 plus delta, they are produced simultaneously. So in these wings, there should be correlation. So between the upper and the lower frequency wing. And this is the upper and this is the lower, so there should be positive correlation here. Then between the lower and the upper, there should also be positive correlation. Then on the diagonal, I mean, a spectral component is always correlated with itself, so you also expect positive correlations. But between the center and the wing, you expect just negative correlation. So if the amplitude here goes down, it will go up here because you take energy away from the center and dump it on the wings. So this is true whether you look for correlations between the center and the upper frequency wing and the lower frequency wing. So this is center and upper, so this should be a minus. Let's do it with a different color. Minus minus here, but also between this, the center, and so this, I should also have a minus here and a minus here. So this is this correlation pattern that we would expect. So this much just so this would then be, this is also an effect that happens on the quantum level. So this you also expect when you look at the level where it's dominated by quantum noise. Okay, so now we can go on. So this is just to remind us, but I don't want to go really much into the detail. Maybe on the next slide I show the nonlinear Schrödinger equation. This is what this NLSE means. It is the differential equation that describes the propagation of the light pulses in the fiber, and it is only called nonlinear Schrödinger equation because it has the same mathematical structure. the Schrödinger equation. So the way this was termed, initially this was an equation in classical optics, so it had nothing to do with quantum, the nonlinear Schrödinger equation. But then, of course, when you quantize fields, it becomes also a quantum equation. Then you call it the quantum nonlinear Schrödinger equation in optics. Okay. Anyway, so here it is. So this is the quantum version. So you see the first order temporal derivative, the second order spatial derivative, and then a nonlinear term where these are basically field operators in this pulse mode. One has to redefine them a little bit. And here you see these three fields that correspond to this chi3 effect. And these are just the numbers, how this scales. This is not so important for the purpose of what we need today. Just to tell you that the time and the x has to do with the one is within the moving frame and the other is the movement of the center of mass of the solitons. So in which precision do you have to look if you are in this regime that you have these solitons of like a few hundred picoseconds? Then in order to have a soliton, you need something like maybe 10 to the 8 to 10 to the 10 photons in the pulse, so that the intensity is high enough for this pulse duration so that this compensation, this cancellation between dispersion and nonlinearity happens so that the pulses stay constant. And that means that the shot noise is the square root of this. Square root of 10 to the 10 is 10 to the 5. Square root of 10 to the 8 is 10 to the 4. So the quantum uncertainty will be observable if you look with a precision of 10 to the minus 4 or 10 to the minus 5, which is possible. So here we are in a regime where the light fields have many more photons than just one. So now if you think that what could happen, and basically I anticipated this on the blackboard here, if you think in a naive first approach that what happens is that you have one amplitude, which the quantum uncertainty just describes one amplitude, so there's basically a single mode and very nice and simple. And this translates into the Fourier domain. You have the Fourier transform of this pulse would be the spectral distribution, and likewise this would just have one uncertain amplitude. Then this is wrong. What happens is what I explained on the board here. This is a similar explanation again, dumping from the center simultaneously in both wings. And then what you can do in the experiment, you can maybe, because the wavelength spread is maybe 20 nanometers, so it's really, for these short pulses, this is really wide, so you can use a grating to disperse them. And then you can look at the noise in the pulse, and by blocking part of the spectrum, you can kind of, and taking all these data, you can measure, and if you analyze the data, then you can determine the correlation between the different parts of the spectrum. So you can determine the interpulse correlations. And by doing appropriate spectral filtering, so without spectral filtering, there is no noise reduction. You don't see noise reduction, as we already expected in this picture where we had this Kerr squeezing with this ellipse, which was tilted such that the amplitude uncertainty did not change. But if you filter appropriately, you can reduce the noise by a couple of decibel. So this is how this is done in the experiment. You launch a pulse into a fiber, you disperse it on the grating, and then you can look in one interval, you can change the frequency interval that you detect, and you can move it around. So when you do this, then you can look for these correlations, and this is a color code. So dark blue is no correlation, reddish is positive correlation, and light blue or greenish is negative correlation. And so basically what you see, we recover more or less this correlation picture. There are some more details here, but this was only a very rude and rough model. So here, this has a tendency to be red on the diagonal. This is where we were expecting these pluses, but also in the upper left and the lower right-hand corner, this is also reddish. And so in between, along the center frequencies, apart from the point where center correlates with center frequency, so here, and there, you see negative correlations. So the structure of these solitons, these quantum solitons, the quantum structure is not so trivial. And when you try to describe this, you find that that you need 3 modes to describe the quantum properties of these pulses. Okay. So in fibers, the nonlinearity is limited. I mean, even if you play these tricks like using these solitons, but I think I mentioned before that when you go to a different scenario like this Bose-Einstein condensates, then you have a similar equation. The nonlinear Schrödinger equation there is called Gross-Bitaevsky equation, but it has the same mathematical structure. So they are the same dynamical behavior, but the interaction is much stronger. So you can explore regimes there that is not so easy to explore in optics here. So with this squeezing, with these quantum correlations, you can create entanglement in this so-called continuous variable regime. And these are early references. The first Einstein-Podolsky-Rosen paper from 1935, this was about the position and momentum. So this was a continuous variable proposal for entanglement. Only later, Bohm kind of translated this to discrete variables with single qubits, with single spins. And then the later ones where this are then concentrated in optics, continuous variable entanglement in optics. You can use these quantum correlations, you can make use of them in quantum interferometry, dense coding, entanglement swapping. I mean, you can do this whenever you have correlation, whether this is in the regime of discrete variables with a few qubits or in the regime where you have highly excited quantum states with many photons. And some applications are, for example, in quantum metrology when you want to measure more precisely and go beyond these limits. There's one thing which is interesting. If you work in the quantum domain, the question is, can I learn something about one quantum object without really, first of all, destroying it? Usually when we measure a photon, we dump it on a detector and it creates electrons and the photon is destroyed. So the same is for light pulses. How can I measure the quantum properties of a light pulse without kind of modifying this light pulse so much that I don't recognize it anymore? And so the story is that also in optics you can do something that we have seen on that picture of these water waves. Namely, you can let 2 optical solitons collide. And so you may wonder how this works, because in this beach there were these 2-dimensional waves crossing each other. Now in the fiber, this is like a 1-dimensional scenario. How could this work? So if these solitons have different center frequencies, their average speed in the fiber will be different. And so if we first launch the slower soliton into the fiber, and then shortly after launch the faster, and if the fiber is long enough that the faster overtakes the slower one, we have a one-dimensional collision between these optical solitons. So the soliton that went in later comes out earlier. Now then, the question is how to measure this, and it's actually difficult to measure because after the collision, the solitons kind of emerge from the collision almost unchanged, as we have seen in this picture of the water waves. And I think the next one is, yes. So this is the same picture again, and there is some information about the collision, which you can also see in this water waves here. And this is that if you extrapolate the ridge from, let's see, this is after the collision, I think. They travel in this direction, this travels in this direction. Yeah. So you see that the ridge, if you extrapolate the ridge, there is this kind of phase shift. So if you would know, if you can do this extrapolation from this phase shift, you can know something by looking at this wave, you can know something about the other wave. So in principle, this is also possible in the optical domain, but this phase is difficult to measure. But there's another thing that one can do, going back to this picture, is if you arrange things such that the collision does not take place in the center of the fiber, but if it is at the very end of the fiber. So there is the collision, and then in the middle of the collision, you exit the fiber, and then you freeze whatever has happened. And while they are interacting, the intensity-dependent intensity of one of the soliton pulses affects the frequency of the other, and vice versa. So by now looking at the shift of frequency of one of these two solitons, which have separate central frequencies, we can learn something about the intensity, the photon number in the other one. And this can be done below the shot noise level, so within the quantum regime. And here you see in the temporal domain what happens in the collision. So there is some interference between these two pulses. And in the spectral domain, you see that the center frequency, they repel a little bit. And if the collision, if you freeze this spectrum by putting the collision at the end of the fiber, you're able to measure this frequency shift, and this frequency shift tells you something about this pulse. Okay, so now back to that squeezing that we discussed. Due to the Kerr effect, this Hamiltonian produces this squeeze ellipse. And Boyd asked me at lunch, maybe this was not so clear, this phi that I had at the board where I said this, if this phi is 2 pi, the whole thing collapses and goes back to the initial coherent state, and there's no effect of this. So the time evolution operator basically images the coherent state onto itself. This phi is the phase shift per photon. Which becomes clear if you look at the equation, because the Hamiltonian was basically it was phi gamma 3 times t, and this I called phi times the photon number squared. So it's clear that this phase shift phi you have when the photon number is 1. So this is the photon number, the phase shift per photon. So but this intensity-dependent refractive index, this nonlinear, more classical nonlinear phase shift, that you have when this phase shift per photon is much less than pi. So there are various ways how one can deal with this. You have this tilted squeezing ellipse, and if you do direct detection, you see still the shot noise, the full spread. But if you send this pulse if this nonlinearity is happening inside an interferometer, inside a nonlinear interferometer, and at the output of the interferometer, you have the appropriate interference. You can shift the ellipse to a position so that the reduced quadrature, this reduced variance, is lined up with the radial direction. And if you then do direct detection, you see this reduced photon statistics. And the way this was done here is that there was an largely asymmetric beam splitter in 1910. So the larger pulse sees the nonlinearity. The 10 times less intense pulse sees much less nonlinearity, and this is just then used to translate the squeezing, which happens to the higher intensity pulse, to translate this so that the squeezing is observable. That was a theoretical proposal initially by Kitagawa Yamamoto in very general terms, and this is a realization with a fiber, with solitons in a fiber. Then, in order to understand this better, we had a collaboration with Peter Drummond and Joel Corney. Again, this is the nonlinear Schrödinger equation with slightly more detail, but we don't want to go into this here. So one thing that happens in a fiber, which I haven't told you, I mean, one thing is that you can describe things ideally with using a theoretical model. And another thing is that you then go and do things in the lab, and then you find what you find. And so what you find here in the fiber, if the fiber is at room temperature, there are phonons in the fiber, and this produces Brion scattering in the forward direction. And this is not very big, but if you look with this precision needed to see the quantum effects, remember this was both in amplitude and phase, was something like 10 to the minus 4, 10 to the minus 5, then this Brion noise is important. Mark Levinson coined this GAWBS, guided acoustic wave Brion scattering. And if you average over these effects here, you will have an effective tilted ellipse where the squeezing is not as high. So this GAWBS reduces the squeezing. Okay. So there have been many attempts to compensate GAWBS with pulses and different techniques. So there's theory. So this asymmetric Sagnac loop is what I showed you before. And one idea is to have pulses, to have a differential technique so that the phonons, the acoustic noise does due to a differential, because if the two pulses propagate through the fiber with a short time difference, then they're not so susceptible to that acoustic noise. So one can play around with this. Another possibility is to say you make the situation a bit more complex. You double the dimension, and instead of having just one mode in one polarization, so if this is a polarization preserving fiber, you have a slow and fast axis. If you launch the light with a polarization which is under 45 degrees to the slow and fast axis, you get two Kerr-squeezed light pulses out at different times if they're launched at the same time. Because the slow and fast axis is called slow and fast because due to the birefringence of the birefringent polarization preserving fiber, the propagation speed is different. So you have these two separate squeeze light modes in these two separate polarization modes. And if you manage to overlap them, then you have polarization squeezing. And that helps, and you can get more squeezing in the end. And instead of launching one pulse under 45 degrees and then getting two pulses out shifted in time, you can also launch two different pulses with a time difference such as to pre-compensate the different propagation time in the fiber for the slow and fast access pulses, such that at the output these two polarizations overlap. And then here you have polarization squeezing or entanglement between these modes. And the nice thing is that if you now you only need to deal with polarization, and there you don't need any local oscillator, and you have access to all these different quadratures. So that's an advantage to go to this more, to double the complexity by going to two modes instead of having just one mode. With this, around 70 dB squeezing was measured. So this is not inferred, that's the actual measured noise reduction. This is the Poincare sphere with which you describe polarization. And so this is a squeeze state living in the Poincare sphere. This is the S1, S2, S3 component. So S3 in our notation is at the northern pole is right circularly polarized light, at the southern pole left circular polarized light. S1 I think is linear, and on the other side the antipode is then linear polarization in the orthogonal direction, and the S2 is then diagonal and anti-diagonal. In order to measure in one particular direction, you can just use half wave plate and quarter wave plates and move these states around to have access to the squeezing direction, the other direction, the anti-squeezing direction, and whatnot. I forgot. Here's the definition. Okay. So basically in the experiment, what we have, typically we have a large circularly polarized component, and then you look from the top, and when you look from the top, it looks a little bit like a two-dimensional phase space and states which are very close to the vacuum. But there is this hidden local oscillator kind of traveling along in this circular polarization, which you look at head-on when you look from above here. And that makes it easier to work with this system and study these Kerr-induced changes of the quantum statistics. That's some tomography that one can do to reconstruct the squeeze state in Poincare space. And then we have done comparison between theory and experiment. And so theory and experiment match well. If the theory, if one takes out this Gauss complication, that opens a little bit more squeezing, not too much, but a little bit. So if we could reduce the Gauss altogether, we could go from the upper curve here to this lower curve. We could move through this red region. And then there's also a problem is Raman noise, Raman scattering in the fiber. I didn't mention this only now. There it's not so 100% clear how far we could possibly go, but this would allow one also to go substantially further down, most likely. But in the meantime, we are also looking at other schemes, and Maria Chechova will tell you about a scheme which is very promising. Okay. So now I'm coming to my final topic, which is the quantum noise and self-induced transparency in a gas-filled hollow core fiber. But maybe I stop here. So this is the third example. So now, so far we talked about parametric processes, non-resonant, far away from any resonant. And now this is about a system where we are very close to resonance. So we have interaction with atoms in order to have a well-defined case and be close to single mode. This is now a hollow core fiber where the light field propagating through the hollow core is just a single transverse mode. And so there we can launch pulses, whatever we want. And then you need to put something inside the hollow core. So you need to put atoms inside. So many people, including us, have experimented with putting alkali atoms into the fiber. So we actually tried this for quite a number of years. I won't tell you how many. And it was not very successful, so then we stopped and then started again after a while. Other groups were a bit more successful, but there's an intrinsic problem, and that is that alkali atoms like to go into glass. So when you go to a bank and maybe they have this thick glass because they're not sure how good a citizen you are, and then if you look at it from the side, often this is polished, it looks very green. And these are impurities in the glass, and much of this are typically alkaline atoms. So when you launch them into this very long, thin hollow core fiber, the diameter, so this is probably, even if this is only like 10, 20 centimeters long, the diameter is probably a few micron. This is mostly surface and almost no volume. I mean, the ratio between volume and surface is incredibly unusual compared to normal cells. So there are many wall collisions, and the alkali easily disappears into the wall. Then Alex Gaeta, for example, at Cornell, he experimented with coating, putting first a coating on the inside of this very thin channel. So then it worked a bit better. Still some alkaline got into the glass, and he applied some special pulse to momentarily get some alkali out of the glass again. And so this was a real problem for a long time, until about a year ago in our lab, and I think it was a visitor. It's very good to invite people to give talks and then take them through the lab and show you an experiment. Sometimes they say, why did you try this? Because they have other things in mind and their background is different. So this visitor said, why don't you use mercury? Then I thought, oh my God, yes, mercury. I know since long times that you can have mercury in a thin capillary and the mercury stays outside the glass. It does not go into the glass. I know. I said, I could have thought of this. Even if the mercury is liquid inside, I mean, the highest possible density. So now this is mercury. So now we put mercury inside and there's no mercury in the glass. It all stays in the gas phase. But the level scheme of mercury is what it is. There's a ground state. So if those of you who are familiar with the earlier days of optical lithography and semiconductor industry, you know that these lines, 254 nanometer, 365 nanometer, are well known in this community because the illumination was done with mercury lamps. Of course, first with the longer wavelengths and then slower and lower wavelengths. And nowadays people don't use mercury lamps anymore, but there was a period when mercury lamps were used. So these are these wavelengths. So this is in the UV. Okay, so it's nicer to have the transition in the visible, but this is not so bad. At least the UV, the air is still transparent. So as you go below 200 nanometers, the air is not transparent anymore. Then you have to evacuate, and then it's getting more complex. But it's kind of difficult to do these experiments at this very short wavelengths. So the transition, so for the self-induced transparency, we effectively need something like a two-level system. And the two levels that we were using is this levels which are connected with this 365 nanometer line. And so there's some splitting, some fine structure splitting, and some fine structure, hyperfine structure in both these levels. Then there are different isotopes. Some of the even isotopes, they don't have this hyperfine structure, but the odd ones do. And then, first of all, you have to get population up here. You can use this only it's no use if the mercury atoms are in the ground state and you apply this radiation, you will see no interaction. So what Ulrich Vogel has done, who is the key person on this experiment, here, this is the first paper out. He has a mercury vapor lamp, and then illuminates, has this part of an elliptical resonator, half an ellipsoid, and in the second focus is the fiber, so that all this 254 nanometer radiation from that mercury lamp is focused onto the fiber, exciting the mercury inside the fiber. Let's go back here. So, going to this transition, and then we, and it's not only this is the main, but the lamp has, of course, all kinds of transitions. So it also brings it in this into the lower level enough. It brings enough atoms in the lower level of this transition, which is connected by this 365 nanometer. The 365 nanometer we create by frequency doubling an external cavity dye laser. So part of the beam we put through the fiber. This is actually some vacuum chamber here. So there we have mercury vapor, and then the whole fiber is evacuated. This is like about 10 centimeter here, this fiber length. And then it takes a while so this is just evacuated. There's the mercury here, so this is heated, so there's mercury vapor. So after a day or two or three, this creeps in. When you have these very thin, long holes, there are certain time constant involved in this. And then you have part of the beam is used as a local oscillator, and only when I came here, I think there's something wrong here. This is, I have to check with Ulrich Vogel somehow. I think this should go up here, because otherwise you would not combine this beam and this local oscillator. But you get the idea. This is a picture of the hollow core fiber, but you cannot see so well, but probably you have seen before. Okay, so then you do a scan. And interestingly, in this 10 centimeter of, there's enough mercury in there that the optical depth is, we have seen numbers beyond 100. So this is extremely, the optical depth is extremely high, which means that the lines are effectively extremely broadened. So this is these are some lines of this 201 isotope of mercury. These are some other isotopes here. And because of this large optical depth, even far out in the wing, you will kind of the vapor is completely intransparent, non-transparent to the light. This is why this broadens so much. Then this shows some Doppler freeze filtration spectroscopy, so to kind of characterize the line and check whether everything is right. And Then and the Ulrich Vogel has modulated the laser and sent pulses in, and the pulses now are adjusted to be like have the area of a multiple of 2 pi, like for example 2 pi, and then you see that the light coming out, the light pulses have a certain delay. So first of all, almost all the light comes out, or even if this is like a 2, 3, 4 times a 2 pi area, so all the light comes out again, not so much is absorbed, and but there is a delay, and this is a very significant signature of self-induced transparency, and so this delay has some power dependence, and this all behaves in the right way. Now, in this case here, at the moment he has seen squeezing slightly off resonance in the wing of the transition. So this is the first squeezing observed in SRT in such a system, and he checked this squeezing by attenuating the light field and see that it behaves in the appropriate way. And so this is quite promising, and we hope to get much more out of the system. But these are very preliminary results. They came out in the last month. Okay, so I think this is what I wanted to show you. So that's the last slide. So these special geometries we use to enhance the effective nonlinearity, and we've been doing this in different systems, and I showed you 3 of them. In this way, the quantum effects are more pronounced, and eventually, one of the perspectives and the future goals is to go into a regime where one has a nonlinearity which is effective already at the few photon level. And for this, another way is that helps might be to focus. And we have one experiment where we have a very deep parabolic mirror focusing light very tightly, and Rojar had a poster here yesterday on some aspect of this focusing, and so this is another route that we are exploring. Okay, so I came to the end of my lecture, so there's more time for discussion.